Hello everybody, in this lecture we're going to talk about sine and cosine when it comes to Fourier series and transform. Why do we choose them as building blocks? This is also an important question. First of all, let us understand the definition of a sinusoid. A sinusoid is basically either a sine or a cosine. It is quite easy. And they have a general form, which I'm about to show you. And we are going to investigate that form actually, which is quite easy. A general sinusoid looks like this. It doesn't matter if it's a sine or a cosine. So we have A times cosine omega t plus theta. This is the general look, and let us actually investigate this a little bit more. The A we have over here is the magnitude of the sine or cosine, and please be aware of the fact that a sine and cosine can actually be in between the values of -1 and 1. Okay, no less, no more, -1 and 1. That's why actually the value of magnitude in here is important, because you are basically multiplying the value of the function here. We also have omega in here, which is the angular frequency, and I'm going to tell you about what angular means in here. Angular frequency, and we also have the phase. This theta in here is the phase. So now you know everything about sines and cosines, because other than these, there's nothing to talk about. Let us start with angular frequency. That's the most important one. So before anything else, in the previous lectures, we made it perfectly clear that sines and cosines are periodic. That's why they also have frequency. What is the relationship between period and frequency? So period is the amount of time required for any periodic function or periodic signal to repeat itself. For instance, a period can be 5 seconds, but frequency is a little different. Frequency is how many times a particular signal repeats itself in unit time, and that unit time is generally seconds. So this is the normal frequency, by the way, the everyday frequency we talk about and we measure in hertz. Right now, I'll just say frequency. It is measured in hertz, and it is the measure of how many times a particular signal repeats itself in unit time. But I also need to mention something. We have angular frequency, not frequency. Why are we talking about normal frequency? Let me explain. Since our sines and cosines are periodic, at the same time they are in circular motion, because circular motion is something quite easy, because a circle starts at one point, it travels the path and comes to the same point. See, it's going to be something like this. This is the starting point. A circular motion starts at one point, travels the path and comes back to the same point, just like periodic signals, because periodic signals repeat themselves. That's why the motion of sine and cosine can be considered to be circular. That's why actually we have angular frequency, because angular frequency means how much angle would you scan per unit time, which is a really important definition. Let me do it again. So I said that sine and cosine, they are periodic. That's why they are circular motion. So since they're periodic, they repeat itself, right? And when they repeat itself, actually, they follow this path. Let's say we have a sine or cosine, it doesn't matter, having a frequency of 1, but 1 hertz, okay? So that means it is going to have it's going to have one cycle in 1 second. Let me actually put it down. One cycle in 1 second. So logically, this means that since it is going to have one cycle, it means that it is actually scanning 360 degrees around the circle, which means 2 pi, because we know the difference between radians and also degrees. 360 degrees is 2 pi radians. So when you have one cycle in 1 second, then it means basically you have 360 degrees scanned in 1 second. And let me also put it this way: 2 pi radians scanned in a second. So this is actually quite easy to understand. You know why? Because angular frequency is how much angle you scanned per second. per unit time, or you can also say unit time because you choose what unit time to be, but it is generally seconds. So logically, if you have a frequency of 1 hertz, this means in 1 second you complete 1 cycle, and 1 cycle is equal to 360 degrees, which means 2 pi radians. Okay, so when you have 1 hertz frequency, you will have angular frequency of 2 pi radians per second. Because the idea is again quite simple, we scan radians angle, right, and we do it per time, right? We want to know it. So 2p radians. So another actually important thing in here, since we know what a normal frequency and angular frequency are, we can easily define the relationship between them. How so? We are easily going to multiply the normal frequency we have by 2 pi in order to get angular frequency. This is the formula. We also know that frequency and period, they're the opposite of each other. I mean, the reciprocal of period is equal to frequency, and the reciprocal of frequency is equal to period, which means that 1 over period is going to be equal to frequency, and 1 over frequency, let's just put it this way, is going to be equal to period. So with that logic, we could also come up with an equation that explains the relationship between angular frequency and also period, which is pretty basic because we're going to say 2 pi times f is equal to omega. 2 pi times 1 over period is going to be equal to omega. So basically 2 pi over period is equal to omega. This is also an important equation, and we could actually rearrange the terms a little bit. Period in here is equal to 2 pi over omega. This is also important. So these equations are all important because we get to know what sine and cosine are up to. And in fact, in order to understand these concepts a little better, let us draw two functions, all right? The first one is going to be x1 of t, which is 2 cosine pi t, and the second one is going to be 4 cosine 2 pi t. So before anything else, the first thing actually that gets my attention is the fact that their magnitudes are different, right? So this x1 function is going to get 4 as maximum, 2 as the maximum value and minus 2 as the minimum value, and this one is going to have 4 as the maximum and minus 4 as the minimum. So right in here also we have the angular frequency. One thing to note is the fact that whatever you have in front of the independent variable is going to be your angular frequency. So here angular frequency is pi, and your angular frequency is going to be 2 pi. So period in here is going to be 2 pi over angular frequency, which is going to be equal to 2, and here the period is going to be equal to 2 pi over angular frequency, which is going to be just 1. So logically, whenever I want to draw a graph for these two, I'm going to do something pretty basic. So both of them are cosines, and cosine is equal to 1 at t is equal to 0. Therefore, with their magnitudes, x1 of t is going to start from here, and also x2 of t is going to start from here, right? So after that, for x1 of t, I see that the period is 2. So logically, if at t is equal to 0, I am at the value of 2. This is important. Here we have 2, and here we have 4. Then logically, after 2 seconds, I have to be at the same place. So let us actually divide this x-axis. 1, 2, 3, 4, 5, 6. I guess that should be enough. So after 2 seconds, we have to be in the same point, and another after 2 seconds. Again, we have to be at the same point, and again at the same point. So it's gonna be something like this. And I know my drawing sucks, but I think you got the idea. This is x1 of t. What about x2 of t? Since it has the period as 1, it's actually going to be a little bit more frequent, right? Because 1 over 1 is 1. This one is having a frequency of 1, and this one is having a frequency of 1 over 2, right? This one has a little bit more frequency, which means that the signal we're having over there is more energetic, right? Because frequency and energy are highly related to each other, they're proportional. So here we have the period as 1. So when it starts from here at t is equal to 1, again, we're going to have the same value, 2, 3, 4. So it's going to be something like this. And I know my drawing sucks, so I'm going to try this one again. All right. So I know this is one of the worst drawings of sines and cosines we've ever had, but you got the idea, right? As you can see, the one with a higher frequency has a higher rate of repeating itself logically. So, and also at the same time, it has more energy. This is the idea of sines and cosines in general. So what about the phase difference? Phase difference is just the shifting in time axis. In here we have, as you can see, theta, which is the phase. Phase is just a way of, shifting your signal to the left or to the right. It's quite easy. It's an easy concept. And since we have dealt with shifting functions from left to right, right to left, all the way down in the way of in the unit of signals, where we manipulated signals. So I'm not going to dive into too much detail right in here because we know what to do. So the question is clear. Why do we choose sines and cosines as the building blocks? So I will actually put a title in here, why sine and cosine are chosen. The reason number 1 is that they're continuous. Yes, they're continuous. So it is actually important to have a continuous signal as a building block because we're going to have a lot of functions and some of them are really weird. Some functions might have a value at t is equal to 1000, for instance. I'm just, making shit up at this point, but functions differ in many ways. That's why it is important to have a continuous function that could be usable in any time on the axis. That's why they are useful. The first reason is that they're continuous. And another reason is that they're also continuous when it comes to differentiation. Because, let me explain to you in this way. Let's say we have chosen a signal like this y of t is equal to t square. So this wouldn't be useful because when I have the first degree differentiation of this y of t, it's going to be 2t, another time it's going to be 2, another time it's going to be 0. So after the third degree of differentiation, it just disappears. However, this is not the case with sines and cosines because when you differentiate sine, it becomes cosine, cosine to sine, sine to cosine. It just goes on like this and it never stops. This is important. And the reason number 3 is that they're periodic. Sometimes we're gonna deal with functions that have different values in different time areas, but whenever you have a periodic function, you would definitely know that that function is going to repeat its action and behavior in one period because it is periodic. It's going to repeat everything. So sine and cosine have no surprise for us in the future because we know how they act in between 0 and 2 pi. So I wouldn't be worried about 8 pi or 10 pi. I wouldn't be worried about that because I know how it acts between 0 and 2 pi. That's why they're pretty useful. That's why we are choosing sines and cosines as building blocks. Let me repeat them and end this lecture. First of all, they're continuous. So this is an important notation. It could be also a discrete function, but it wouldn't be logical and useful. Then we have the advantage of differentiation, which we don't have anywhere else. Some of the students say, what about an exponential function, teacher? And in the next lecture, by the way, we're going to see the relationship between exponential function and sine and cosine. So they're basically the same thing. That's why I understand your proposition, which is a really good one, but we're going to see the relationship between sine, cosine, and also exponential function. And the reason number 3 is that they are periodic, which is pretty useful. So this is going to be the end of this lecture. If you have any questions, please do not hesitate to ask anytime you like. I will always be here to help you out. Thank you so much for watching and see you in the next one.